Okay, so let's get started on lesson 11. What we just finished was lesson 10, where we solved systems of equations by graphing. Didn't really define system, but it just means more than one equation. In our case, it's always going to be two equations. What did we look for when we graphed our two equations? The intersection point, and that guy right there, that point was called the solution. Now there's some downsides to doing this kind of problem graphically. Number one, it takes time, right? Graphing takes some time, and you had to graph two different lines. Number two, probably more important, is that everything you do is approximations, right? And so we saw some variations in the answers, like people sitting next to each other got different answers that were close, and that's fine. But one of the weaknesses of the graphical method is that it doesn't necessarily give you the exact answer. And here we're going to cover two methods to solve the same kinds of problems, but these ones will give us the exact answer. In fact, they won't rely on graphing at all. We're not going to draw any pictures here. But in the back of our mind, we'll recognize, okay, there's just pictures floating around in these problems, even though we're not looking at them. Okay, summary. In this lesson, we solve systems algebraically, not graphically, which is what we did in our previous lesson, using two methods, substitution and elimination. All right, so here we're just going to kind of point and watch. There isn't anything for us to write down on this page. It's all written out. So here's the substitution method. We'll see elimination very soon. All right, there's our system of two equations. The first step in part A is to solve either equation for either variable. That gives you four choices. You could solve the first equation for x, or the first equation for y, or the second equation for x, or the second equation for y. You can do any of those four things. But if you know what you're looking for, you can sometimes save yourself the aggravation of fractions. If you solve the first equation for x, the first thing you do is what? Solving this guy for x. I need to move this negative 2y by adding 2y. That's fine. Then it's going to say 6x equals. How do I solve for x? Divide by 6, which gives you fractions all over the place. Yes? You'll have to divide by 6. If you solve the first equation for y, you'll end up dividing by negative 2 fractions. If you solve the second equation for x, you'll divide by 4 fractions. If you solve the second equation for y, no division. We see that? Because the magic number in front of y is 1. Now, we don't always have that to go for, but if you have it and you don't go for it, you are introducing fractions where you don't need to. So in this case, you solve for y by subtracting 4x. And we get that. Everybody buy it? No fractions. Okay, here's the key step for substitution. Once you have solved one equation for y, you take what you got and you substitute it into the other equation. We just used the second equation. We are now going to plug into the first equation. And we're going to change that y into this y, which is really 5 minus 4x. And that's what's happened right down here. So take a look at this first equation. It says 6x minus 2y. Now it says 6x minus 2 times yellow highlighted stuff. But that's y, right? The highlighted stuff is the same as y, so this is perfectly legitimate. Change your y into something which is equivalent to y. 5 minus 4x goes right in there. Notice the parentheses, gotta have them. Equal negative 3, still equals negative 3. Questions on that step? I'll highlight again. You got to make sure you substitute into the other equation. If you wanted to, you could change this y into 5 minus 4x because that's what y is equal to. But if you do that, all the letters will cancel and you get something which is true, like 5 equals 5, but that doesn't help you. So always plug into the other equation. Okay, moving down here, the nice thing about this equation in part B is it has only x in it, only one variable, which makes it better than all the equations up above. And then you solve this equation for x in the normal way. In this case, what do we have to do first? We got to get rid of those parentheses by multiplying the 2, right? So you distribute the 2 and you just get friendlier equations. We're not even going to look at the details here, but you can all solve that equation. I have confidence. And we get x equals a half. X equals a half oftentimes is the end of the problem. You found x, you're done, you move on. But in this case, the problem had x and y. And every problem that you just solved for me earlier today, you gave two numbers as your answer, right? You always gave an ordered pair. So you don't stop when you get x equals a half. You got to find y. There is one really good place to go to find y, and that is right there. Because if you just plug in x equals a half, let's do that right here. X is a half. If you just plug a half right there for X, you do your arithmetic and you get Y equals what? I think it's 3. Yeah, that's written down here. So there's the 5 minus 4x, and we just change the x to the half that we found, and we do the calculation and we get 3. So our answer is x equals a half, y equals 3, or like you guys did earlier today, half comma 3 in parentheses. Questions on the process? All right. This isn't going to be mandatory for us, but if you have time, you'll want to check your answer, and you should be able to plug 1/2 and 3 into not just one equation, but both of the original equations and get things that are true. So in this case, the first equation ends up being -3 equals -3, it's true. Second equation, 5 equals 5, it's true. That means we actually did find the solution and we didn't make a mistake. If you get something that isn't true, you made an error someplace. I don't know how to find where the error is. You kind of have to go back to the beginning and just read each line again. But if you get something that's false there, that's a clear indication that there's a mistake. That is called substitution. On the next page, we'll see something called the elimination method or the addition-subtraction method. Here's the process. Take a look at the new system of equations. 9x plus 6y equals 54, and 6x minus 5y equals 9. That's our new thing we're going to solve. If we were to solve one equation for one letter, which was the first step of the substitution method we just saw, is there any way to avoid fractions? What's that? You could find something in common. That's what we're going to do. Yeah. 9 and 6 do go into 54, but ultimately, if you solve the first equation for x by dividing by 9, you're going to end up with a 6 over a 9, which is a fraction. And because there's no 1s in front of any of the x's and y's, you're going to end up dividing no matter what you do. To be honest, whether or not I have to do fractions completely determines whether I do the substitution method or this other method. And I can look at that and say, all right, we're going to get fractions no matter what letter we solve for. I'm not going to do substitution. I'm going to do this alternative. Okay, let's do something that is valid but not helpful. We're going to add these equations up. You guys buy? We can add an equation to another equation and get a third equation, which is valid. If you have something like this, 3 is equal to 1 plus 2, everybody agree? And 12 is equal to 3 times 4, yes? If I add the left-hand side, what do I get? 15. I'm just going to copy the right-hand side. It was 1 plus 2, and then adding the right-hand sides, I just get 1 plus 2 plus 3 times 4. Is it true? Of course, it's 15, right? Equals plus equals gives you equals. So we can add these guys even when it's not just numbers, but it's x's and y's. And if I add 9x and 6x, and I'm just intentionally going column-wise because that's where the like terms are, 9x and 6x is 15x. And what about the y's? Plus y equals 63. That is a valid equation. But it isn't any better than the two equations I had, right? It still has 2 letters in it, and that's the problem for us. You could solve for y without the fraction. I don't think I would go this route to get to a substitution. We're just going to do this differently, but you could avoid fractions now. Okay, so the point here, equals plus equals equals equals. Equals plus equals gives equals. The idea is that that equation isn't great because it still has x and y. But what we're going to do is manipulate the original equations so that when I add up the new equations, one of those variables is going to cancel. So we'll get rid of that guy. It's not helpful for us. Follow along with me. It'll become clear why we're doing what we're doing in a moment. But I'm going to decide to multiply the first equation by 2, both sides. Don't worry about where the 2 came from. We'll see it soon. But as long as I do the same thing on both sides, legal, yes? Multiply both sides by 2 is perfectly valid. So we're going to distribute this 2 in here. So what do we get? 18x plus 12y equals, that 2 has to hit the right-hand side as well, both sides. 108, everybody buy that equation is valid. It's equivalent to the first equation. Then we're going to multiply the second equation by -3. Again, don't worry about where the numbers came from, but we'll see something good, and then we'll figure out the numbers. Multiply here, we get -18x here. plus 15y, that's there, and then mine equals minus 27 divided by the second equation. It's equivalent to the original second equation. We know equals plus equals gives equals. If you add these equations, what happens to those x's? They cancel. Let's add the y's. How many? We got 27y equals, and we add here 1, 10, 81, I think. Yes? Is that equation better than the ones we started with? Yes, because it has only one letter in it, right? Solving from here is pretty straightforward. You just solve for y, divide both sides by 27, and you get y equals 3. To find x, this actually isn't as easy as it was on the previous step because there's no, on the previous page, there's no equation that just says x equals something with y in it. So here, you're just going to go to any of the original equations. I'll go to the first one and plug in the y equals 3. Just change the y to the 3. That equation becomes 9x plus 18 equals 54, and you could solve that for x, yeah? The details are written on the page. I don't want to worry about those. So what was what's the last mystery we need to uncover here? Yeah, so x is going to be solved at the bottom, but what's the mysterious thing that we haven't discussed? Yeah, the 2 and the negative 3. But you can see what we were going for. We were going for getting rid of one of the letters, x in this case. So we made it so that the 9x and the 16x both turned into the same number, but one was negative, right? So 9 and 16 both go into what number? What's the smallest number 9 and 6 both go into? 18. And so you just multiply by whatever you can to make them both 18, but make one of them negative. Just as well, we could have played a different game where we aim to get rid of the y's. 6 and 5 both go into what number? 30. So your goal, if you wanted to do this problem again and get rid of the y's, is to turn them both into 30, but one negative. So what would you multiply that first equation by to turn into a 30? It's 5. You multiply everything by 5. And the second equation to turn it into a 30? 6. Yeah? Positive 6 or negative 6? Yeah, it's already, I like the fact that I have one positive and one negative. I always want it to be one positive and one negative. Okay. So that is that. X, Y, check your answers. We're not going to do that. Going back, multiply to eliminate the y's. Yeah, okay, I think we talked about that. Let's fill it in here. Again, trying to get rid of the y's. What are we multiplying the first equation by to turn into a 30? There's a 5 there. Second equation times 6. The y's will cancel after you do that work out. Is it clear why we call this the elimination method? Right, we added two equations and we eliminated a variable. Sometimes it's called the addition subtraction method, again, because you're adding equations. You could subtract equations, but we'll just add every time. So two completely different methods to solve the same kinds of problem, substitution and elimination. I need you to get good at both of these guys. Oftentimes, we provide more than one way to solve a problem, and I just say, hey, just pick a way and get good at it. Like we looked at mx plus b, and we also looked at the y minus y1 equals mx minus x1. And I said, I'm never going to force you to use one over the other, except on homework where we have resources. Right, so on tests and quests, I'm not going to force you to use one over the other for mx plus b or the other guy. I just said pick one and get good at it. I need you to get good at both of these. On a test or a quiz, I feel comfortable asking you to do one solution, one system with the substitution, and then another system with elimination. The reason that I'm changing my tune here, whether you choose mx plus b or the y minus y1, I think it's about the same amount of work. I don't think there's like any problem that it's like easier to use one over the other. So that's why I just say pick one and get good at it. But here, I think that there are some times where the problem is much easier to use one method over the other. And so I want you to have both tools in your toolbox so that you can pick the easier method based on what the problem is. Okay, last thing in the demo here is some special cases. Number 5. Usually two lines intersect at a single point. but there are two special cases we looked at in our previous lesson. Two parallel lines where we had no solution, or two lines that were really the same line where we had infinitely many solutions, right? Now, if you guys were doing the graphical method, and you actually graphed these two lines here, and you saw that they looked parallel, and you'd say, oh, they're parallel, there's no solution. Or if you drew the lines and you ended up drawing the same line twice, you'd say, oh, it's the same line twice, and there's infinitely many solutions. But I'm not asking you to graph anything in this lesson. And so what we need to do is understand what to look for while we're doing either substitution or elimination that's going to tell us that we're in one of these special cases, parallel or the same line, because you don't have that visual to rely on if we're using this new stuff here. So number 6 says use substitution to solve each of these systems. Something strange will happen when you solve, and then make some conclusions after you've read 7 below. So let's do this together. We are going to do substitution on part A. Y equals 2x plus 1, y equals 2x plus 3, that's our system. Substitution, first step is to solve one equation for one letter. In this case, that is done, right? The first equation is already solved for y. Great. And then we're going to substitute that into the other equation. So instead of the y that we have down here, what are we going to put? 2x plus 1. Right, we're just going to substitute that right there for the y. So this guy becomes, instead of the left-hand side, 2x plus 1 equals 2x plus 3. Okay, we all see the substitution that just happened? Okay. Now this is a very strange equation to solve, because when you subtract 2x from both sides, what happens? I'll put minus 2x. Minus 2x, what do we get? 1 equals 3, which is a very strange thing to see in a math class. And so, like I said, something funny happens. If you get a funny thing like that, where all the variables disappeared, that's your cue that we're in one of our two special cases, which is either parallel lines or the same line twice. If you get a ridiculous equation like 1 equals 3 that is obviously false, which one do you think you're in? We're in the parallel. Because 1 equals 3 has no solutions, right? It just isn't true. And so we're in that parallel case where there are no solutions. And so that's written right here. If you end up with a false statement such as 7 equals negative 2, then there are no solutions to the system. That's our conclusion up here. No solutions is the answer to this system. Okay, let's try part B. Y equals 2x plus 1, 6x minus 3y equals negative 3. Again, we're going to do substitution. We're going to solve one equation for one letter. Which equation would you solve? Top or bottom? Solving one equation for one letter. Everybody would solve the bottom one? One of these equations is already solved for one letter, yes? That's what I want us to do. So which equation are we solving? Top equation for x or y? For y, because it's done. You could solve the bottom equation for x if you want to. It's going to be messy. So if you've got a gift already handed to you, take it. Right? That first equation already has y solved for by itself. So we're doing the same thing where we substitute. Instead of the y in the second equation, what are we going to put? 2x plus 1. Right? That is going to go right in there for the y. Okay, so I'm going to copy that whole equation. 6x minus 3 times. But then instead of y, what are we putting? 2x plus 1. Notice the parentheses. We got to have them. We're changing y into something that's big. It's still one thing. It's still a y. It's in parentheses. Equals? Negative 3. Right. That's what we'll get. Everybody see the substitution that we did? And then we'll clean it up. Let's see what happens here. 6x, and then we'll distribute that minus 3. So what's the next thing I'm writing? minus 6x, and again distributing the minus 3. Minus 3 equals negative 3. And then again, strange thing happens, the x's cancel. 6x minus 6x disappears, and we're left with what equation? Negative 3 equals negative 3. Doesn't mean we did anything wrong. It just means we're in one of these special cases. If the x's all disappear, you're either in parallel or same line. Not our usual case, which is just intersecting lines that have one point in common. Jake? Yes, you absolutely could. I never even thought of that. What a great question. I mentioned earlier that when you do substitution, let's go back to an example that's a little bit trickier than the one that we're on. We solved the second equation for y, and then we replaced the y in the other equation. But Jake is remembering correctly that I said if you go ahead and replace the y in the same equation that you just used, all of the variables will disappear. And in this case, you want to see it? If we decide to change this y into a 5 minus 4x, it's legal, right? And that's what y is. So I'm going to copy 4x plus, instead of y, what are we putting? 5 minus 4x. And what's after the equals? It's a 5. 4x minus 4x cancel. And what do we have left? 5 equals 5. So if you don't follow my advice where I said plug into the other, you will look at that and say, oh, special case because the x is canceled. It's either parallel or the same line. But it isn't a special case. There is one answer to this problem. This is just an ordinary two intersecting lines problem. So it's a great observation, Jake, that if you're not careful, you will get tricked into thinking you're in one of the special cases, because this will happen every time if you do substitution and you plug into the equation that you just used initially. Okay, all right, so let's get our conclusion here. In orange, we had 1 equals 3. Our conclusion was parallel lines and no solution. Here we get negative 3 equals negative 3, which is always true. That's the other case, the other extreme case. We're actually looking at two lines that are exactly the same. If you were to graph y equals 2x plus 1, and then on the same piece of graph paper, graph 6x minus 3y equals negative 3, you would end up graphing exactly the same line. How many solutions does that system have? Infinitely many. So that's our conclusion here. Infinitely many solutions. And that's written out right here. If you end up with a true statement such as 4 equals 4, there are infinitely many solutions to the system. Right? Two special cases. The way that you know you're in one of those special cases is all the variables disappear. Questions on that? Okay, so we've got about 12 minutes. Move on to the next page. You're going to get as far as you can on the activities today, and then we'll pick up here in a future class.